this is it, folks. I think I'm ready to try to explain that, like what's going on with the QFT without the mathematics. But this is still a bit exploratory, so I don't know if I'm going to be able to. Let's just so this is what I did now is I did a bit of a different example. Let me just I'll just remove the I think I'll just remove this. Okay, I'll just remove this and so what I did here is I tried a bit of a different example where it's not completely a square. It's kind of, I don't know. I mean, it's not just like a plus one minus one plus one minus one. Like you've got this step in between, so it's a bit of a different, bit of a different, bit of a different wave. I wanted to see if here we can see a bit. Uh, we can see what happens. And the result in this case is the following, right? But what I want to do now is I want to play with two things. Because what seems obvious to me, right, is what I said, that it's sort of a similar concept like with Grover's algorithm, the search, quantum search. If you remember that, if not, just go and check the video out of the Grover's algorithm explained without the maths. I think it's a similar concept where now you have this, right, and then I've encoded something in the phases, in the phase. So I've encoded the wave, right? If What would happen if I were to come back to? So I want to apply now Hadamard's everywhere. Let's see. Interesting. So basically, those those values we're left with are the ones that we've kind of flagged in here. Z. What if I don't do that? Yeah. Yeah. Because hmm, because if you remember well, that was a similar. So that was kind of the idea with Grover's algorithm, right? It was that once you've now got some negativity, some negative uncertainty, then you cannot go back to the 0, 0, 0, 0 state. The trick with Grover's algorithm is that you are just flagging one element. So because you're flagging that element, it was then kind of trying to go back to zero to zero zero zero, but it was not. Um, but it was not completely possible because of that. So this is a similar concept. The idea that you're creating uncertainty, then messing with it and turning some of these uncertainties, so some of this superposition into a negative, and then trying to go back, and then that creates this effect. Now, the thing here is you don't have any more positive and negative uncertainty. You have, I don't know if you can call it sort of complex uncertainty. I should patent that maybe. The idea being that it's this. So the example of this sort of um, red cases where you've got uncertainty that it's nor it's like it's in between positive and negative, right? Um, so that makes it probably hard to explain. Okay, but if we go back, so if we know that if we now try to go, like we apply all the time Hadamard's, right? All the time Hadamard's. That's what we get. We get the elements that we have flagged in here. It's not entirely the ones we flagged. It's 110, 110, because this is, because if I were to use a Z here, that's the one we get, but because we use just a half rotation, kind of get a superposition of both. Yeah. Not so sure, but anyway, so what this algorithm, so what the QFT does is, instead of doing just that, it's playing with the phase in between those Hadamard gates, right? So what we're saying is no. It's saying no. We don't do this. We don't do this, but we do this. And I will let me maybe play with this. I'm trying to kind of decompose the algorithm, see what's kind of happening between what would happen if the algorithm would go differently. So I'm trying to understand. I'm trying to kind of make variations of the algorithm to see if I can grasp really what's happening. The other thing is, I find it pretty interesting that the exact those angles, right, is like pi divided by 2, pi divided by 4, pi divided by 8. I mean, those are definitely powers of 2, right? Maybe I'll try to change them, see what happens. Yeah, so in this case we're at the same spot, because obviously we haven't that's a zero. So this qubit is not containing. So the qubit 0 does not contain any of the phase information, any of the wave information in this case. So all those things are zeros, so nothing happens. Okay. So we might as well not even do that, right? But and now if we now do this here, but it's between 2 and 3, and between 2, no, 1 and 1. Exactly. What has happened now? Okay, so let me remove those Haramards. I think they're not giving me they're making the picture worse. So how could I interpret that? Basically, because it's this in this particular example, this doesn't have to happen, right? So because there's no information in there that is useful for us. The Hadamard must be there, because if we don't apply the Hadamard, then we're that's nice. Okay, so and maybe so with this in mind, pi divided by 2. So this is the starting point. So when we apply the Hadamard here, right, we get rid of half of the elements, but the rest stays. So we're this basically what it does is like it just packs back the certainty in this case, and because there's no there was no phase. Uh, okay, so because there's in this case there is no this particular qubit didn't encode any relevant information. Whatever now we do with rotations doesn't matter. So I'm going to ignore this for the second. But I think the concept is you take back the uncertainty, but then what you are doing with the but then you got to rotate. So you got to basically make up for the information that you've lost. I think. But why? Why? Hmm. For example, now we will add another Hadamard here. So that's qubit 1, okay? And so this means, it's a tricky one to explain, right? But what is this doing? What is this really doing in this case? Because now we've got like a kind of a square signal, right? So it seems like it's flattening. But now when we will add the control rotations, when we are adding the control rotations, here and here, but this way. Whoop. So it's trying to what this is intuitively doing. I think it's trying to kind of it's trying to keep. It seems like it's trying to keep the it's trying to keep the information, but with less samples intuitively, because here we've got like this pattern, right, where in this case between 0, 0, 0, 0, 0 and 1, 0, 0, 0, like we're giving a full circle, like we're giving a full round, right? um we're giving a full round, and then whereas here we're missing one more state to get the full round. And if we go back to the original state, that's also what's happening, right? You see. So we've got these two. So this here, right, between 0, 0, 0, 0 and 1, 0, 0, 0. So we're also here giving almost two full rounds. So of I think that's intuitively what's happening. So what the QFT is trying to do is it's trying to compress the information. So um, it's trying to basically remove the samples by remove elements of the superposition by applying the Hadamards. So you go back to not to superposition with less possible states, and then making up for the information. So for the information we've lost, kind of trying to make up for this by rotating the other qubits so that we keep the same pattern, right? And so intuitively, if you do that to like to the very end, then you will have packed the information so much that effectively what you have at the end is basically peaks of, so you've got like the peaks where the where this, I feel uncomfortable by saying the word frequency because I'm not really familiar with waves, and so I might be saying like crap right now, but I think this is really what's happening. I mean, you can correct me if you think I'm wrong, but I think intuitively that's what's happening. I mean, I didn't find any intuitive explanation anywhere else, not even in the O'Reilly book. So this is really me just playing with a concept that I have, an idea that the way that I see this, right? And maybe if someone says no, you're totally wrong, just let me know. But I think that's what's happening, right? So you see, basically, you're trying to represent the same, okay, but with, so you're trying to keep, with these rotations, you're trying to keep the same pace, because if we don't have these rotations, it's kind of the same, but it's yeah, but you're missing. So this has doesn't have as much information as the other one, because it's like this is now a square one, right? So you wanna have those rotations for the sake of yeah, okay, because if you don't have that, then you're gonna do the next Haramar, then you're gonna lose everything. So you don't want to lose too much. Probably that's the idea. Probably that's the idea. Okay. Okay. So interesting. Here. And now the next one. So now you do this Haramar, boom. So you're now losing again information. Mm, 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 again information. And now you wanna again correct for what you've lost, and you wanna apply another. And so here it's already, I think, quite. I don't know if my explanation holds in here. And then you plan a hard mark, and then something's not right. Mm, could it be those things? Those things are. I don't think those were needed. If I come back to this, so that was 4. Am I missing something? No, this stays the same. Am I missing something? Yeah, maybe that's the result actually. Which could be the result, because where am I? QFT, QFT, QFT. So this. Yeah, that's what you have. So basically that's kind of the result. Okay. So if you go to the measurement probabilities, it's composed of frequency 2, 4, a little bit of those ones. Okay. Interesting. State vector. because really, if we go back to the to the to to this here, and we kind of encode now the um, this one or this one, just this one back here. So really, all what we need to do here, and like I'm ignoring the first qubits because I know that this doesn't have any impact on the algorithm, is basically that you're basically doing Hadamard. So you're kind of, and now you have to account for the information that you've lost, and now you're doing another Hadamard. That's what you end up with? No. Let me do the whole thing. Control rotation, control rotation, control rotation. It's just this is between this and this, and it's a 4. I should will be faster here, and this is between U and 3, and it's an 8. And then we copy the same, but it's Hadamard 1. This is 2, 3, and this is non-existent, and this is 1, 1. And now we are taking this and doing Hadamard 2, and this is between 3 and 2. And then we are doing a Hadamard 3. So I was wrong in the sense that I was saying you can just skip things, because here it is definitely important to note that this operation you cannot skip it, because there is a control Z that is actually touching that element which has the phase encoded. So that's important, actually. Yeah, that's important. So I take that back, but still the explanation I think is the valid one. So so if you know what I mean, right? So if you and here the same, you just can't remove this. Okay, it is indeed having some effect. So conclusion. The QFT iterations, like, they must be all there, so don't remove them. This is again one of the mistakes where you try to think in terms of classical computation, and you're like, oh yeah, but that's not affecting the subsystem and whatever. Here it's a bit more delicate because qubits affect each other from all different sides. So yeah, but let's do a last run. So you just to make sure that this whole thing makes sense. I'm gonna copy that and copy that. Yeah. So we are here, right? So we've now lost information, and now we're basically going to we're basically going to rotate that. So it apparently still nothing maybe happens, but it's quite crazy. Hmm. It's like it's one of those things that it just might apply it just might start working out once you add the other stuff. That's the funny thing. Because you've literally entangled those qubits. Yeah, of course, you've entangled them. So now, if you're going to modify this one, this is going to have effects. Yeah, blah. That's pretty crazy. So in the next step, we're doing this, but we said is in 1, and this is in 2 and 4 and 1 and 1. Exactly. So if you see, right, we're trying to keep the same structure, right? As I said, like with every time we lose the information, we're trying to keep the same pattern, but with less samples, with less elements in the superposition. So you're kind of packing everything up. So it's really follows a similar concept like Grover's algorithm in terms of this playing with certainties to just pack the information, like not amplify, but it's like condense all the information in the states that you have left. And so, sorry, that is wrong. Why is it not right? This is the control. This is the control. Okay. And now we're going to do the next step, which is this one. So we again, we're again packed, but remember that here we're trying to, there are 2 full cycles, right? So there was +1, -1, +1, -1, so 2 full cycles. So we're trying to keep that information in there by rotating, but because we're already running out of possible states, it starts being kind of impossible. And so when you do that, everything gets packed into. I mean, that's because those are the two frequencies it's made of already. So you can't. Okay, so that doesn't let you go back to just having one frequency. So that's basically, I think that's what's happening. So again, to recap, so with the Hadamarts, you're basically removing. So what you're intuitively trying to do is you're trying to you have a set of samples that encode a wave in a superposition. Then with Hadamarts, you're trying to remove the amount of states, and then with the rotations, you're trying to kind of recover the phase information, so your wave information. And so you're effectively kind of compressing that until you cannot compress it anymore. So what you're left with is a sample set that has the peaks of your frequency, so the peaks of the information that you've been trying to pack. This is something that it seems that makes sense to me, but it can also be totally BS. So don't go blindly and trust that. If you have a different opinion or you have a different perspective to this, let me know, because I think that can help me as well try to understand that better without the maths behind. And the reason the angles are working this way, I mean, it seems to me this is just because of so you're doing this with the leftover qubits. So you're doing this to the power of 2. I somehow don't feel that's totally 100% like a strong non-mathematical explanation, but I'm going to leave it here for now. If I read, so if I see, if I come up with something else, then I'll definitely make another video on this, especially that I'm going to be using QFT in the future a lot for other stuff. So I'll definitely come across that concept more often. And so I'll definitely make a correction if I see that it's needed. Perfect.